last few lectures we have discussed stationary perturbation theory, also called the Rayleigh-Schrodinger perturbation theory. And there we saw that the Hamiltonian had two parts. One was the free Hamiltonian H naught, and then there was a perturbing Hamiltonian H prime, and H prime itself was not a function of time, and that is why we refer to that as time independent perturbation theory or stationary perturbation theory. Now today I would like to discuss the salient features of time dependent perturbation theory. That simply means that H prime is a function of time. This is one case where time dependence is brought in because the perturbation has a time dependence in it. Of course, there are other situations in reality where you really do not think of it as a free Hamiltonian H naught plus a perturbing Hamiltonian H prime, which is a function of time. Instead, you could think of a situation where the total Hamiltonian is essentially the same, except for a period of time when it changes to something else. So I will not be discussing a situation of that kind. I would instead be looking at a situation like this, where the free Hamiltonian is not a function of time, and then there is a perturbation which is a function of time. This is clearly a straightforward generalization, well, as straightforward as it can get, of what we studied in the Rayleigh-Schrodinger perturbation theory, where we saw the linear Stark effect and the Zeeman effect. Now you would also recall that in one of the earlier lectures, in a different context, we looked at the shell model of the nucleus. There we discovered that if you put in the spin orbit coupling L dot S as an extra piece in the Hamiltonian, degeneracies are lifted, and in fact you find that the total angular momentum J is a good quantum number, and the magic numbers in the shell model are explained pretty reasonably, provided you do not go to higher magic numbers. The lower ones like 2, 8, 20, etc. are described very well, explained very well and justified, provided we introduce the spin orbit coupling term in the Hamiltonian. Now there too there was no time dependence, but you should now be able to connect up that shell model of the nucleus with what we did in the Rayleigh-Schrodinger perturbation theory, because the term in the potential which lifted the degeneracy was the time independent spin orbit coupling term. So in fact you have seen three examples of stationary perturbation theory. One is the linear Stark effect, which came because we had an external electric field, and then the Zeeman effect, you could have used a magnetic field, and of course the shell model of the nucleus, where the spin orbit coupling helped lift a degeneracy. Now in contrast we have this, where H prime is a function of time. The aim of course is to find psi, any state which is expanded in the relevant Hilbert space of the problem. The aim is to find psi of t. Now if you look at the Schrodinger equation, you simply have IH cross delta delta t of psi of t is equal to H psi of t. The general solution of course would be u of t comma t naught psi of t naught, where u is a unitary operator. I will call it the time evolution operator, and psi of t naught was the initial wave function that was given, the initial state of the system that was given to us. So of course you need to find out u in order to find out psi of t given psi of t naught. And then you know the wave function at time t. So, that is one aspect to time dependent perturbation theory, where you could expand this in powers and look at the time dependence. There is something else which can happen, where I really do not use perturbation theory at all, where in contrast to this, I have a situation, say a 2-level atom. This atom interacts with, say, laser light, the radiation field, the coherent state, which is the laser light, and suppose the frequency omega of the radiation field exactly matches the frequency difference between the ground state and the excited state. Then its resonance, and it is possible that all the atomic population in the ground state, initially in the ground state, just move up to the excited state. Clearly, this is not a situation where I will use perturbation theory. Instead, I simply have a model of a 2-level atom, if you wish, where a population, an atomic population in the ground state just moves up to the excited state at some instant of time and then comes back, and this could be a process which keeps on happening in cycles. Now, such a situation is also a time dependent effect. As time changes, the population, atomic population in the ground state moves to the excited state and then comes down, and so on. So, there are very many situations where one has to deal with a time dependent problem. So, the first thing that I wrote was this, where I have a unitary operator and I wish to find what the unitary operator is. The second thing is scattering theory, where the Hamiltonian itself changes over a small period of time. And then the third thing is where I do not use perturbation, but I talk of an effective 2-level atom model, where the atom gets excited and goes to the excited state and then comes back to the ground state because of interaction with the laser light. So, these are all various examples of time dependence dynamics. So, today what I would like to look at is the laser atom interaction model, which I spoke to you about last. So, I would be looking at a situation first where I have a radiation field in free space, and it is a single mode radiation field. So, I model it by an electric field which is E naught cos omega t, and omega is the frequency that I talk about. Now, this is an interaction with the atomic dipole operator. I am using the dipole approximation, and therefore, H prime is minus d dot E, which I can write as minus d dot E naught cos omega t. So, this is what I have. I have an atom which can be treated essentially as a 2-level atom, for the reason that I told you a little while ago, because if this energy is E and this is Eg, E minus Eg by H cross is omega naught. So, this energy difference is H cross omega naught, and near resonance, that means omega approximately equal to omega naught, the population in the ground state just moves up only to this level, and the other levels can all be forgotten. This is not a perturbation. This is simply a situation where there is population transfer between two levels, and above all, there could be an instant of time, plausibly an instant of time or a set of times, where the population, which was initially only in the ground state, completely moves up to the excited state. In contrast to the kind of perturbation theories that I have spoken about till now, where essentially the state is the original state of the system with some perturbations, which could be the first order correction, second order correction, third order correction, and so on. Let me emphasize, in contrast to what we learned earlier, where the state at any instant of time is largely dominated by what was initially the state before perturbation, and perturbation simply makes some corrections to the state. In contrast to that, here we have a situation where the initial state can completely change, in the sense that if initially the atomic population is in the ground state, it moves up to the excited state at some instance of time, and therefore it is majorly populated only in the excited state. So it is not a correction to the ground state. I will first look at this model. It is called the Rabi model, and we have the initial basis states G and E of the atom, the two level atom, and of course they evolve as eigenstates of the original Hamiltonian H naught, so that at any instant of time the state of the system, the state of the two level atom, would be some coefficient e to the minus I e g t by h cross ket g plus C e of t e to the minus I e e t by h cross ket e. This is understandable because at that instant of time that we are considering, ket g would have evolved in this manner because it is a stationary state. Ket e would have evolved in this manner, but you should be able to write the wave function as a superposition of the evolved states at that instant. There is no reason to believe that these coefficients cannot depend on time. Indeed, in general they will, and that is why the state has been chosen in this manner. Now, but we also know that this is true h naught plus h prime of t. Remember that h prime of t is minus d dot E naught cos omega t. Now, if this is the Schrodinger equation and we plug this in, what do we have? We have IH cross delta by delta t Cg of t e to the minus I e g t by h cross ket g plus Ce of t e to the minus I e e t by h cross ket e. That is the left hand side, and that is equal to h naught plus h prime of t Cg of t e to the minus I e g t by h cross ket g plus Ce of t e to the minus I e e t by h cross ket e. So, this is what I have. Now, if I differentiate here, for instance, there are two terms that depend on time. Cg itself is a function of time, and therefore I will get a Cg dot, where the dot stands for the derivative with respect to time. And of course, this also gets differentiated. Remember that ket g itself is not a function of time, it is the initial basis state. So, if we did that, we just have IH cross Cg dot of t e to the minus I EGT by H cross ket G. Let us keep the IH cross out of this. The next term is minus I EG by H cross e to the minus I EGT by H cross CG of t ket G. Now similarly I have to differentiate this and I get plus CE dot of t e to the minus I EET by H cross ket E minus I EE by H cross e to the minus I EET by H cross CE of t ket E. Now this, first of all, H naught acting on ket G pulls out an EG, CG of t EG e to the minus I EGT by H cross ket G. Similarly, H naught acting on this term pulls out an EE, okay, and then I have H prime. So H prime, remember, is an operator. It is the it has the atomic dipole moment d in it, plus H prime. So I am going to write this as plus CG of t e to the minus I EGT by H cross H prime ket G plus CET e to the minus I EET by H cross H prime ket E. So this is what I have. Now one thing is clear, I can take this equation and flank it with ket E on this side and also ket G on this side, on the left hand side. Now that should give me something. So let us see what happens. So if I started with ket G, certainly the first term survives, because ket G is normalized to 1. Similarly, this term also survives. But these two terms disappear because ket G and ket E are orthogonal states, and therefore these two terms do not contribute. Here it is the matrix element of H prime, but this will be 0 because you will recall from our discussion, even in the case of the Stark effect, that the dipole operator cannot connect states of the same parity. Similarly, E H prime E is 0, but what survives is G H prime E, and therefore its complex conjugate. So we were at this point, and here you can see that this term will survive, this term will survive. Here G H prime G is 0, but G H prime E will survive. So if you look at these terms on the right hand side, you have CG of t EG e to the minus I EGT by H cross. That term survives. This goes, but this survives. This is what I have. Of course, I can bring the IH cross to this side. Look at what I have here. I have minus IEG by H cross, Cg of t e to the minus I Egt by h cross. So that goes, and I am left with Cg dot of t. Of course, I can write this as Cg dot of t e to the minus I Egt by h cross equals this object here, minus I by h cross Ce of t e to the minus I Eet by h cross. This object, let me call it nu, and let me say that that is also equal to its complex conjugate, because generically this is real, as you have seen from our discussion of the Stark effect earlier. So there is a nu. It is not just nu, there is a nu cos omega t, where I have used the fact that the dipole operator between G and E, this dipole operator actually minus the dipole operator between E and G dot E naught, I call that nu. What is left behind is simply a cos omega t, which I have put out there. So now if you look at this, Cg dot of t equals minus I by h cross nu cos omega t e to the minus I. That gives me, if I take this to that side, it gives me a minus I E minus Eg by h cross, and therefore I just have an e to the minus I omega naught t Ce of t. So this is my first equation. This is what I have. Similarly, I can get Cg, like I got Cg dot of t, I can get Ce dot of t. And how would I do that? Instead of using a bra G out there, I will put a bra E. Use the same facts that these quantities are 0 and that G and E are orthogonal kets. And then I will be left with another analogous equation. This is the equation Cg dot of t, and I will have another equation for Ce dot of t, which I merely write down and which you can easily get by doing precisely what I did earlier. So I will have Ce dot of t is minus I by h cross nu cos omega t e to the I omega naught t, that is one difference, Cg of t. So these are the two equations that I have. These are coupled equations. I can decouple them and get an equation just for Ce and another just for Cg by taking the differential once more. Now if I did that, I get the following thing. So let us look at Ce of t. So Ce double dot of t is minus I by h cross nu cos omega t, but now one should be careful. There is a Cg of t as well. I want to use an approximation. Now this approximation is the following. I write cos omega t as e to the I omega t plus e to the minus I omega t by 2, club it with e to the I omega naught t, and as I said, the physics of the situation is this, that you are working with omega very close to omega naught, and there are only two levels involved. There is therefore a priori no reason to retain terms of the form omega plus omega naught in the exponent. The relevant frequency, the contributing frequency, is really omega minus omega naught. So this object is going to be approximated to e to the I omega naught minus omega t by 2. Now if I did that, Ce double dot of t is minus I h cross, or let me first write Ce dot of t, it is minus I h cross nu, there is a 2 h cross from here, e to the minus I omega minus omega naught t Cg of t. So, this is an approximation also called the rotating wave approximation, but I will not get into those details here. However, the reason why this approximation is made is precisely that the original state of the system is not what is preserved. There are two levels that are involved, and the population can jump between these two levels. And the laser is tuned so that omega is very close to omega naught. In fact, you define something called a detuning parameter delta, which is essentially this difference, omega minus omega naught. And if delta is 0, you are at resonance, and omega approximately equal to omega naught, you are near resonance. So, it is the near resonance situation that we are considering here. So, look at this equation and now take the second differential. I get a minus I omega minus omega naught e to the minus I omega minus omega naught t Cg of t, and then there is another term which is e to the minus I omega minus omega naught t Cg dot of t. Once more here I will use the rotating wave approximation, and I will only retain the exponential term which has omega minus omega naught and not omega plus omega naught. So, this Cg of t is substituted for in terms of Ce dot of t. Then I have a Cg dot of t here, which gets written in terms of Ce of t, and therefore I get a decoupled second order equation, Ce double dot of t related to Ce dot of t and Ce of t. So, here is the second order differential equation that I have for Ce. I have Ce double dot of t plus I omega minus omega naught Ce dot of t plus 1 by 4 h cross squared nu squared Ce of t is 0. You see, when I plugged in for Cg dot of t, I had an e to the minus I omega naught t, and that I would have put in here, and then I would have used Cg of t in terms of Ce dot of t out here, and I would have put that in here. So, it is in this manner that I eliminate Cg of t and I get an equation like this. Want to start with a trial solution for Ce of t. This seems like a reasonable trial solution for the following reason, that you will recall that we wrote psi of t as Cg of t times this plus Ce of t times this, and since the external electromagnetic field varies like a cosine function, I would expect a sinusoidal variation in this as well, and therefore it is a reasonable thing to start off with a trial solution where Cg of t and Ce of t vary like e to the I lambda t, and that is why this solution for Ce of t. Now, if it does not work, it will show up as a contradiction somewhere else, but at this level it is merely common sense that has guided this choice of trial solution, because the field varies sinusoidally, and therefore I will expect the response to vary sinusoidally. Now, once you put in for Ce of t here, there is a Ce double dot and a Ce dot. This second differential will bring down a lambda squared. The first differential brings down a lambda, and then of course there is an e to the I lambda t, but the e to the I lambda t will cancel out all over, and you just have a quadratic for lambda. So, there is a lambda squared, it is an equation which involves lambda squared, lambda and a lambda independent term, and therefore it has two roots. I will leave this to you as a simple exercise. Just plug in Ce of t to be that and obtain the value of lambda. As I have already mentioned, delta is an important parameter in atom optics. It is the detuning parameter, and that is what appears here. Nu, you will recall, is simply the matrix element of the dipole operator between the two states E and G times an E naught. The two roots of lambda are these. There is an overall half, and there is a delta plus minus this object. Look at this. Delta squared has the dimensions of frequency, and so does nu squared by h cross squared, and therefore to the power of half has the this delta squared has dimensions of frequency squared, and so does nu squared by h cross squared. When delta is 0, if you are at resonance, this drops out. What is left behind is nu by h cross, and that is an important thing to remember. The matrix element plays a role there, the matrix element of the dipole operator between the ground state and the excited state. But in general, of course, these are the two solutions. What would I expect for lambda? A general solution, it could be either of these, and I will call the two roots lambda plus and lambda minus. And then, of course, the general solution for Ce of t can be written down A e to the I lambda plus t plus B e to the I lambda minus t. This is where I impose my initial conditions. I start by saying that the ground state is populated, the excited state is not populated. This is at time t equals 0. So, when I said time t equals 0, it is clear that A equals minus B, and therefore, the solution Ce of t is A e to the I lambda plus t plus minus e to the I lambda minus t. So, this is what I have for Ce of t. I can use the initial conditions and fix A, and A turns out to be minus 1 by 2 h cross nu delta squared plus nu squared by h cross squared to the power of minus half. Now, given Ce of t, one can always find Cg of t up to a phase, because modulus Ce squared plus Cg squared should be equal to 1 as the wave function is normalized to 1. So, I can substitute for A, substitute for the lambdas, and I have an expression for Ce of t, and therefore for Cg of t, and therefore for psi of t. Now, this is what I have for a solution for psi of t. What does this tell me? It tells me a very important thing. First of all, I identify something called a Rabi frequency. The Rabi frequency itself comes from here. It is delta squared plus nu squared by h cross squared to the power of half. So, in terms of the Rabi frequency, I can ask what is the probability of the system being in the excited state, what is the probability for the system being in the ground state, and so on. I identify the Rabi frequency omega sub r. The nomenclature itself comes from historically from nuclear magnetic resonance ideas. I identify it to be delta squared plus nu squared by h cross squared to the half, and then C of t and Cg, Ce of t and Cg of t take on these simplified expressions. This is just a bit of algebra, and I leave it to you to verify this. It's a straightforward piece of algebra. The important thing to note here is this: apart from an e to the I delta t by 2, Ce of t depends on time as sine omega r t by 2, and Cg of t has a cos term and a sine term. Now, suppose the detuning parameter is 0, that means omega exactly matches omega naught. Then you can see if delta equals 0, Ce of t is I nu by omega r h cross, where omega r is now given by nu by h cross. You see, set delta equals 0 and that gives me a nu by h cross. So I can, that too cancels out and I just have an I. Since delta is 0, this does not contribute, this is just unity sine omega r t by 2h cross. So that is nu t by 2h cross out there. And what about Cg of t? Cg of t is cos nu t by 2h cross. This is 1 and that is a 0 there. So this is what I have. I have some very simple evolution dynamics for this system. So what is the probability that, well, at time t equals 0 it is clear that Ce of 0 is 0 and Cg of 0 is 1, which is as it should be, those were our initial conditions. So the population was completely in the ground state at time t equals 0 and then it oscillates sinusoidally, because I can now ask what is the probability that the system is in the excited state at any instant of time. Well, that is sine squared nu t by 2h cross. And this is interesting because surely when sine squared nu t by 2h cross takes a value unity, which it does for t equals pi h cross by nu, then Ce of t mod square equals 1. In other words, the probability of being in the excited state is 1 and the probability of being in the ground state at that instant of time is 0. So there is a complete population transfer, that is the nomenclature that is used. There is a population transfer from the ground state to the excited state, but it does not stay there, because again later on when sine squared of the argument is 0, the probability of being in the excited state becomes 0 and the entire population is in the ground state. So what do we see? We see this happening. When the detuning is 0, we see that it moves from the ground state to the excited state sinusoidally, then back from the excited state to the ground state, then from the ground state to the excited state and so on. So if you look at the dynamics, it is a complete sinusoidal variation. And this is the Rabi model, and you can talk of a Rabi frequency of oscillation, because all said and done you have a Rabi time pi h cross by nu, and corresponding to that there is the Rabi frequency of oscillation. This is the Rabi frequency nu by h cross. So this is a simple model, if you wish, where the time dependence is studied not using perturbation theory, but saying that the system moves from the initial state to just one other state, and all the dynamics is between these two states in such a manner that at certain instants of time the system could have a probability 1 of being in the excited state and 0 in the ground state. This is called the Rabi model, and it deals with a single mode radiation field in free space interacting with essentially a 2-level atom. Now instead of working with the free space, you could talk of the radiation field confined to a cavity. The cavity could be an optical cavity, a microwave cavity, whatever it is, the radiation field is confined to a cavity and it interacts with atoms in that cavity. Normally these would be multi-mode radiation fields, but as a simple example I would like to take a single mode radiation field in a cavity, and therefore I will not use E is E naught cos omega t. I will be more particular about what I write for the electric field inside the cavity, and inside this cavity there can be photon creation and destruction. So, I move on to the next model of interaction of the radiation field with matter, with atom, and this would be the Jains Cummings model. So, let me move on to this model. As I said, the electric field now is written in this form. A and A dagger are the photon destruction and photon creation operators respectively, and in one of the earlier lectures where we looked at the electric field in the cavity, we did arrive at this expression. So, I would urge you to go back to that lecture and see how exactly we got this. This is the polarization vector, and this is in some arbitrary direction E, and therefore, if you look at H prime, which is minus d dot E, I write this as minus d dot E out here, this E, that is a scalar product, and then I have grouped all these constants h cross omega by epsilon naught v to the power of half sin kz as P. This set of constants, V is the volume of the cavity, epsilon naught h cross is the Planck's constant, omega is the frequency, and epsilon naught is the permittivity, and so sin kz, because I started with this electric field. And then there is an A and an A dagger. This is the expression which is familiar to you, which we have derived earlier. And now if you look at this, you have this electric field, which is, in terms of operators, it is essentially A plus A dagger. And this is supposed to interact with the two-level atom operators. And what are the two-level atom operators? First of all, the Hamiltonian itself would now have three parts, which is H naught of the atom plus H naught of the field. This is the free field Hamiltonian, that is the free atom Hamiltonian, plus H prime, which involves the interaction between the field and the atom. So, let us write down these terms one by one. H naught field is simply H cross omega A dagger A. That is what you will have if the photon creation operator is A dagger and the destruction operator is A and the frequency is omega. This is H naught field. Now, what about the atom? Now, as far as the atom is concerned, look at the various operators. Again, from one of my earlier lectures, I defined sigma plus as this operator, sigma minus as sigma plus dagger, and therefore as this operator, and sigma 3 as this difference. Now, we checked out that this satisfied the SU2 Lie algebra. Now, one thing is for sure, if sigma plus acts on G, it takes it to E. Similarly, if sigma minus acts on E, it takes it to G, and so on. This is what I have. Now, what happens if sigma 3 acts on G? Sigma 3 acting on G just gives me a minus G, and sigma 3 acting on E gives me a plus E. So, suppose I had the reference level 0 here in energy, and suppose the ground state had energy minus h cross omega naught by 2, and the excited state had energy plus h cross omega naught by 2. Surely I can write the free atom Hamiltonian very simply in the following manner. As h cross omega naught by 2 sigma 3, because what happens? Sigma 3 acting on G gives me a minus sign and ket G, and therefore picks up an energy minus h cross omega naught by 2, and sigma 3 acting on E picks up a plus sign in front of ket E, and therefore gives me energy h cross omega naught by 2 sigma 3, and therefore this is H naught atom. And then of course I have minus D dot E. So look at H prime. H prime essentially has this atomic operator dotted with the electric field. How do I model the atomic operator? What does it do? First of all, D should not connect states of the same parity. So suppose D were of the form A times sigma plus B times sigma minus, where A and B are some constants. What would it do? D acting on the state E, this operator acting on the state E, let us forget the vector sign, the operator acting on the state E by D, by this D I mean D dot E, polarization vector, and therefore I have made a scalar of it. So this is A sigma plus B sigma minus. This is 0, this is 1, and therefore I get Bg. And therefore GDE is B. It is non-vanishing. On the other hand, if D acts on G, it will take it to E, and this term will be 0, and I get an A, but one is the Hermitian conjugate of the other, and therefore I will remove this and I will just say it is Eg plus Ge. So that would be my argument for writing the operator D in terms of sigma plus and sigma minus. So D is essentially sigma plus sigma minus, and then I need to worry about the interaction. So I need to do a D dot E, and the operator in E was A plus A dagger, and therefore the interaction Hamiltonian itself can be very trivially written now. H prime is essentially, I can write it as some H cross lambda for dimensions, sigma plus sigma minus times A plus A dagger. But if you now look at the combination, what are the terms? This gives me term sigma plus A, sigma minus A, sigma plus A dagger, sigma minus A dagger. Sigma plus takes the atom from the ground state to the excited state. In the process, a photon has been absorbed. Sigma minus takes the atom from the excited state, brings down the atom from the excited state to the ground state, releasing a photon, but this is the photon destruction operator. Now that cannot be. A photon has been created, and therefore this term is not, on physical grounds, this term cannot be put in. Now look at this term. Sigma plus absorbs a photon so that G goes to E, then the photon is not created. Again, on physical grounds, this term cannot be there. So what survives here is simply sigma plus A and sigma minus A dagger. I'll continue from here next time. In fact, I have given you the various parts of the Jains Cummings Hamiltonian. There is a free radiation field, there is a free atom Hamiltonian, and then the interaction term. We'll proceed with the Jains Cummings Hamiltonian tomorrow and look at the various interesting features that appear using this Hamiltonian.